Welcome back to A Quieter World. Tonight, we will explore Yosemite, moving through it in the same steady way the land itself has changed, shaped by gravity, pressure, and the slow movement of the earth beneath our feet. If you find these long, calm science stories useful, you can like the video and subscribe for more. If you choose to leave a comment about where you are listening from, it is always interesting to see how far these stories travel. Now we begin. Yosemite is often encountered as a place of sudden scale, where granite walls rise sharply and open spaces feel almost oversized. What feels dramatic today is the surface expression of processes that worked quietly for immense lengths of time. To understand why Yosemite looks this way, it helps to begin far below the surface, before there were cliffs, valleys, or even mountains. The visible landscape is the final result of deep systems that started underground. Around 100 million years ago, molten rock formed deep within the Earth's crust, along the western edge of North America. Scientists believe this magma was generated as tectonic plates interacted offshore, allowing heat and material to move upward into the continent. Instead of erupting at the surface, this molten rock cooled slowly underground. When magma cools this way, it forms granite, a rock made of tightly interlocked mineral crystals. Slow cooling matters because it changes the texture and strength of the rock. When magma cools quickly, crystals stay small and weakly bonded, but slow cooling allows large crystals to lock together, much like a tightly packed mosaic. In Yosemite's granite, quartz, feldspar, and mica form this interlocking structure. People often describe granite as hard, but what really matters is how evenly its minerals share stress across the rock. At the time this granite formed, it was buried beneath several kilometers of overlying rock. The pressure from this weight acted like a heavy lid, keeping the granite compressed and stable. For tens of millions of years, nothing about this granite hinted at cliffs or domes. It existed as a deep, hidden foundation, strong but unseen. Over time, tectonic forces began to change the region. Scientists estimate that the Sierra Nevada rose not through violent folding, but through the slow tilting of a massive block of crust. You can think of this tilting like lifting one end of a long table. One side rises gradually, while the other remains relatively low. As the eastern edge lifted, the western side stayed gentler, creating the broad slope that now descends toward California's Central Valley. This tilt mattered because it raised the granite closer to the surface. As uplift continued, erosion went to work above it. Wind, rain, and flowing water slowly removed the layers of rock that once covered the granite. This removal happened grain by grain and drop by drop. Over millions of years, kilometers of material were stripped away, reducing pressure on the granite below. When pressure is released from rock that formed deep underground, the rock responds by expanding slightly. This expansion does not happen evenly, and that unevenness causes fractures. Scientists call this process unloading. It works a bit like opening a vacuum-sealed container, where the contents subtly shift once the pressure is gone. In granite, unloading produces curved fractures that roughly parallel the surface. These fractures are important because they define how large pieces of rock can later separate. Rather than breaking apart randomly, the granite begins to divide into broad sheets. Gravity can then pull these sheets away over time, even without help from ice or rivers. At the same time, Vertical and horizontal joints formed as the granite responded to cooling and regional stress. These joints created internal planes of weakness without destroying the overall strength of the rock. The granite became something like a strong loaf of bread with natural slices already outlined. It remained solid, but it was no longer uniform. These fractures mattered because they became entry points. Water could seep in. Temperature changes could act on them. Icy conditions would later grip them. As uplift continued, rivers began flowing across the rising landscape. Water naturally followed zones of weakness, so early rivers traced paths along fractures and joints. River erosion works by concentrating energy into narrow channels. Sediment carried by water acts like a grinding tool, slowly wearing down the rock beneath. At this stage, Yosemite's valleys were narrow and V-shaped. This shape reflects the focused nature of river erosion, where cutting happens mainly at the channel bottom. People sometimes imagine rivers carving grand landscapes on their own, but research suggests rivers are better at starting valleys than finishing them. These early valleys mattered because they established direction. They set the routes that later systems would follow. As valleys deepened, relief increased. Slopes steepened, and gravity became more influential in shaping exposed surfaces. Rockfalls occurred where fractures intersected, especially along newly exposed faces. Detached slabs accumulated at the base of cliffs, temporarily shielding lower rock from erosion. Over time, these fallen blocks broke down or were removed, exposing fresh granite. This cycle repeated slowly, maintaining a balance between exposure and resistance. Chemical weathering played a limited role in Yosemite's relatively cool and dry climate. Instead, physical weathering dominated. Daily temperature changes caused the rock to expand and contract slightly. Seasonal freeze and thaw cycles allowed water in fractures to freeze and expand, gradually widening cracks. Scientists observed that these processes did not dramatically reshape the landscape at this stage. Instead, they prepared it. Each fracture widened a little. Each valley deepened slightly. Each slope grew steeper. Time is the thread connecting all of this. Granite formation took millions of years. Uplift unfolded over tens of millions more. Erosion never stopped, but it never rushed. Scientists reconstruct this history by combining mineral chemistry, fracture geometry, and regional tectonics. The evidence points towards slow, layered change rather than sudden transformation. By the time climate conditions began to cool, Yosemite had already become a high granite landscape. Its rock was exposed, fractured, and elevated. This preparation mattered because cold climate forces do not invent landscapes. They reshape what already exists. Elevation allowed snow to accumulate. Valleys provided pathways. Fractures provided leverage. The granite's strength meant that once steep walls formed, they could persist. The structure beneath the surface quietly controlled what would happen next. One detail that often surprises people is just how thick the original overlying rock once was. Scientists estimate that the granite now visible in Yosemite formed beneath as much as 8 to 10 kilometers of material, meaning the rock we see today was once buried deeper than the height of Mount Everest. That depth explains why Yosemite granite is so uniform and strong. The intense pressure acted like a long-term clamp, squeezing out weaknesses and allowing crystals to grow slowly and evenly. Another interesting detail is that granite does not become exposed everywhere in the Sierra Nevada at the same rate. Yosemite happens to sit where erosion removed overlying rock particularly efficiently. exposing the granite earlier than in surrounding regions. This early exposure gave rivers more time to carve into the surface before colder climates arrived. In effect, Yosemite received a longer preparation period than many nearby landscapes. People often think of mountains as static, but research indicates the Sierra Nevada is still rising today, albeit very slowly. This continued uplift subtly maintains elevation, helping preserve steep relief rather than allowing it to soften over time. What makes Yosemite distinctive is not any single process, but the timing. Granite formation, uplift, fracturing, and erosion all occurred in an order that maximized contrast. Had uplift happened faster, the rock might have fractured differently. Had erosion been slower, valleys might have remained shallow. Instead, the sequence aligned in a way that produced strong, exposed granite at exactly the moment other forces were ready to act. By the end of this phase, the land was not finished, but it was tuned. The foundation was complete, and the next system was already waiting. Once Yosemite's granite landscape stood high, exposed, and fractured, climate became the next controlling force. Over the past 2 to 3 million years, Earth entered a period marked by repeated swings between colder and warmer conditions. During colder intervals, snowfall in the Sierra Nevada increased, while summer melting decreased. Scientists say that when snow survives year after year, it stops behaving like weather and starts behaving like geology. Fresh snow is light and full of air, but as new layers accumulate, the weight compresses the layers below, squeezing out air and forcing snow crystals to change shape. Over time, snow turns into firn, a dense transitional material, and eventually into solid glacial ice. Researchers estimate this transformation can take decades to centuries, depending on temperature and snowfall. This change matters because ice is not rigid in the way people often imagine. Given enough thickness, ice flows. Glacial ice moves under its own weight, slowly deforming rather than sliding like a solid block. A useful way to think about it is like very cold honey, moving so slowly that the motion is invisible moment to moment. Inside the ice, crystals stretch, rotate, and slip past one another. This internal deformation allows glaciers to creep down slope under gravity. In Yosemite, valley glaciers likely moved anywhere from a few centimeters to more than a meter per day. That pace sounds slow, but over centuries, it becomes relentless. One interesting fact is that glaciers flow faster in their centers than along their edges. Friction with valley walls slows the sides, causing the ice to stretch and crack near the margins. These cracks form crevasses, which are surface expressions of stress inside the ice. While many crevasses are hidden today, their former presence influenced how ice interacted with the valley walls. As glaciers moved, they stayed in constant contact with the granite beneath them. This contact is what allowed ice to reshape the landscape. Glacial erosion operates mainly through two mechanisms, abrasion and plucking. Each works differently, but together they are exceptionally effective. Abrasion happens when rock fragments frozen into the base of the glacier scrape against bedrock. These fragments come from earlier rockfalls and from material already removed by the glacier itself. As the ice moves, these rocks grind against the granite like coarse sandpaper. Over time, this process smooths surfaces, rounds edges, and leaves behind fine scratches called striations. Striations are important because they record the direction of ice flow. Scientists still use them to reconstruct how glaciers move through Yosemite. Abrasion is most effective beneath thick, steadily moving ice. Over thousands of years, it can lower valley floors and polish entire cliff faces. Plucking works differently and depends on the fractured nature of the granite. Meltwater at the base of a glacier seeps into cracks in the rock. When temperatures drop, that water refreezes and bonds pieces of rock to the base of the ice. As the glacier continues moving, it can pull those blocks free. This process is especially effective where temperatures hover near the melting point of ice. Evidence suggests these conditions were common beneath Yosemite's valley glaciers, plucking leaves behind steep, jagged surfaces, while abrasion smooths and rounds. The contrast between these two textures can often be seen on the same rock face. Together, abrasion and plucking transformed Yosemite's early river valleys. Narrow V-shaped valleys were widened and deepened into broad U-shaped troughs. This change in shape reflects how glaciers fill entire valleys from wall to wall, unlike rivers that concentrate erosion at the bottom. Yosemite Valley itself was reshaped by multiple glacial advances rather than a single event. Scientists believe at least 4 major glaciations affected the region. During the largest of these, ice in the main valley may have exceeded 1 kilometer in thickness. That is roughly the height of 3 stacked Empire State Buildings. Ice of that thickness does not simply follow terrain. It overrides smaller features, presses outward against valley walls, and amplifies relief. As the ice pressed against the granite walls, it steepened them into near-vertical cliffs. The strength of the granite allowed these walls to remain intact once carved. Meanwhile, glaciers flowing through smaller side valleys did not erode as deeply. When the ice melted, these tributary valleys were left hanging above the main valley floor. This mismatch in erosion depth explains why many of Yosemite's waterfalls drop so dramatically. The height of the falls reflects glacial carving rather than tectonic uplift. While valleys were being reshaped, granite domes were being refined. These domes formed earlier through unloading, but glaciers modified their surfaces. Where ice flowed smoothly over curved granite, abrasion enhanced the dome's rounded forms. Their upper surfaces became polished and gently sloped. On the downstream sides of these features, plucking often dominated. This produced steeper faces, where blocks were removed rather than smoothed. The contrast between smooth and sheer surfaces preserves evidence of ice movement, much like fingerprints left behind after the glacier vanished. As glaciers advanced, they carried enormous amounts of debris. Rock was transported within the ice, beneath it, and on its surface. When glaciers melted, this material was deposited as till. Till is an unsorted mixture of clay, sand, gravel, and large boulders. Unlike river sediment, till is not arranged by size. Everything carried by the ice is dropped together when melting occurs. Till accumulated across valley floors and along slopes, smoothing irregular surfaces and filling depressions. In some places, it still forms the foundation beneath meadows. Where glaciers paused or stabilized, debris piled up into ridges called moraines. These ridges mark former positions of the ice margin. Terminal moraines formed at the furthest advance of a glacier. Lateral moraines formed along the valley sides where rock fell onto the ice from above. In Yosemite, scientists use moraine locations to estimate past ice extent and climate conditions. These ridges act like frozen snapshots of former glaciers. Moraines also influenced what came next. They redirected meltwater, dammed valleys, and shaped where rivers would later flow. As climate warmed, glaciers began to thin and retreat. Retreat does not mean glaciers moved backward, but that melting outpaced forward flow. As ice margins shrank upslope, meltwater flowed beneath and alongside the glaciers, carrying sediment downstream and further shaping valley floors. By around 15,000 years ago, most valley glaciers in Yosemite had disappeared. Only small alpine glaciers and persistent snowfields remained at higher elevations. What remained was a landscape deeply reorganized by ice. Valleys were broader, walls were steeper, and surfaces were smoother than before. Ice did not erase the granite foundation, it amplified it. The fractures prepared earlier determined where ice could grip and remove rock. The strength of the granite preserved dramatic vertical relief. By the time ice released its hold, Yosemite's form was largely established. The next forces would work within boundaries set by glacial carving. One detail researchers often point out is how uneven glacial erosion can be, even within the same valley. Ice does not carve at a constant rate, but responds to slope, thickness, and underlying fractures. Where ice thickened or slowed, pressure increased and erosion intensified. Where it thinned or flowed faster, carving weakened. This uneven action explains why Yosemite contains both deeply scoured basins and relatively untouched rock nearby. The result is a landscape shaped not by uniform force, but by shifting conditions within the ice itself. What looks balanced today is the outcome of constant adjustment beneath moving glaciers. After ice retreated from Yosemite's valleys, water became the dominant moving force. Unlike glaciers, water responds quickly to seasonal change, yet it still works within pathways carved over thousands of years. Much of Yosemite's water begins not in rivers, but as snow. Each winter, moist air from the Pacific rises over the Sierra Nevada, cools, and releases precipitation. At higher elevations, this precipitation falls mainly as snow. Snowpack matters because it acts like a natural reservoir. Instead of releasing water all at once, it stores it for months, gradually feeding rivers as temperatures rise. Scientists estimate that in heavy snow years, Yosemite's snowpack can contain the equivalent of several meters of liquid water spread across the landscape. That stored water determines how rivers behave long after storms have passed. As spring arrives, sunlight and warmer air begin to melt the snowpack. Melt does not happen evenly, but responds to slope, elevation, and exposure. South-facing slopes receive more sunlight and melt earlier, while shaded north-facing slopes release water more slowly. This staggered melting smooths out river flow over time. Water released from melting snow moves downhill under gravity, following the lowest available paths. These paths were already established by glacial carving. In effect, glaciers built the plumbing, and snowmelt now supplies the flow. Meltwater gathers into small streams that merge into larger rivers. In Yosemite, the Merced River is the primary drainage, flowing westward through the main valley. Rivers differ from glaciers in how they move sediment. While ice carries everything together, water sorts material by size and weight. Fast-moving water can lift sand and small gravel, while slower flow allows heavier particles to settle. This sorting shapes riverbeds and influences channel stability. An interesting detail is that rivers often carry more sediment during rising flow than during peak flow. Scientists attribute this to fresh material being picked up as banks are first inundated. As rivers cut into the landscape, they also respond to obstacles left behind by glaciers. Moraines and till deposits can redirect channels or create temporary basins. In some cases, meltwater pooled behind moraine ridges, forming short-lived lakes, As these lakes drained or filled with sediment, they left behind flat valley floors. These flat areas later became meadows, but at this stage they functioned primarily as sediment traps that slowed water movement. Waterfalls are among Yosemite's most recognizable features, and they exist because of uneven glacial erosion. Hanging valleys, left high above the main valley floor, now deliver water abruptly downward. When water drops freely through air, it converts gravitational energy into motion. The height of Yosemite's waterfalls reflects the depth of glacial carving rather than the volume of water flowing over them. Some waterfalls flow year-round, fed by large drainage basins and sustained snowpack. Others are seasonal, roaring in spring and fading by late summer. Yosemite Falls, one of the tallest in North America, can exceed 700 meters from top to bottom. During peak snowmelt, its flow can increase by more than 10 times compared to late summer. Waterfalls also play a role in erosion, though in a more focused way than rivers. At the base of a falling stream, turbulent water scours plunge pools. These plunge pools deepen over time, especially where rock is fractured. However, in Yosemite's hard granite, erosion at waterfall bases proceeds slowly. Another interesting observation is that waterfalls migrate upstream over time. As plunge pools deepen, rock collapses at the lip, slowly shifting the waterfall's position. Downstream from waterfalls, rivers settle into broader channels. Here, flow slows, sediment drops out, and riverbeds stabilize. The seasonal rhythm of Yosemite's rivers is pronounced. Peak flow usually occurs in late spring or early summer, driven primarily by snowmelt rather than rainfall. In contrast, late summer and autumn flows depend on remaining snowfields and groundwater seepage. By late season, many smaller streams run dry. Groundwater plays a quieter role in Yosemite's water system. Some meltwater infiltrates fractures in the granite, moving slowly through the subsurface before re-emerging downstream. This delayed release acts like a savings account, storing water temporarily and releasing it during drier periods. While limited in volume, this groundwater helps sustain base flow in rivers. Scientists note that Yosemite's rivers are highly responsive to climate variation. Small changes in snowpack can produce large differences in flow timing and intensity. In warmer years, snow melts earlier, shifting peak flows forward and reducing summer water availability. In cooler years, melt stretches later into the season. These changes affect not just water levels, but sediment transport. Earlier melt can produce flashier flows that move more material in shorter bursts. Sediment movement matters because it reshapes channels, alters habitat, and influences flood behavior. Over time, rivers adjust their form to balance water and sediment supply. Despite their constant motion, Yosemite's rivers remain constrained by glacially carved valleys. They cannot easily change course or widen dramatically. This confinement increases flow energy during peak melt, enhancing erosion in some areas while depositing sediment in others. Water does not erase the work of ice, but refines it. Rivers smooth valley floors, redistribute material, and connect high-elevation snowfields to lower landscapes. By the end of this phase, Yosemite's water systems had settled into a seasonal rhythm. Snow accumulated, melted, flowed, and drained in predictable patterns shaped by elevation and exposure. The landscape now operated on annual cycles layered over deep geological time. Each spring repeated processes established thousands of years earlier. Water had taken control of daily change, but it remained guided by structures carved by ice. The next systems to respond would depend directly on these water-driven patterns. Another detail that often goes unnoticed is how temperature controls not just how much water moves, but how it moves. Cold meltwater is denser and flows differently than warmer summer runoff, subtly changing how energy is transferred to the riverbed. In early spring, snowmelt is cold and fast, behaving like a heavy liquid sliding over stone. Later in the season, warmer water becomes more turbulent, stirring sediment rather than simply pushing it forward. Scientists observe that this seasonal temperature shift influences how gravel bars form and migrate. Early flows tend to clear channels, while later flows rearrange what remains. Water moving through Yosemite's valleys also interacts constantly with air. As rivers rush through narrow sections, they entrain oxygen, increasing turbulence and mixing. This mixing matters because it affects how sediment stays suspended. A useful way to picture it is shaking a jar of sand and water, where motion keeps particles from settling. In calmer stretches, the shaking stops and gravity takes over. Sand and gravel drop out, gradually rebuilding the riverbed. These alternating fast and slow sections create a repeating pattern of riffles and pools. Riffles are shallow, fast-moving areas, while pools are deeper and slower. This pattern is not random. It reflects a balance between slope, flow speed, and sediment size that scientists see repeated in mountain rivers worldwide. Another interesting fact is that Yosemite's rivers do not simply cut downward. In many places, they also migrate sideways within the limits of glacially carved walls. This lateral movement allows rivers to rework their own deposits, shifting channels slightly from season to season. Think of it like a rope sliding back and forth across a narrow groove. Even small shifts matter over time. They determine where sediment accumulates and where banks are reinforced or undercut. Waterfalls introduce yet another layer of complexity. As water plunges downward, it breaks into droplets, increasing surface area and energy exchange with the air. This breakup accelerates evaporation and cooling, especially during peak flow. On warm days, waterfalls can locally lower air temperature near their base. Researchers have measured microclimates around large falls, where moisture and temperature differ noticeably from surrounding areas. These conditions influence where mosses and algae later establish. At the top of waterfalls, water spreads thinly over rock before dropping. This thin flow is highly sensitive to changes in volume. A small increase in meltwater can dramatically widen the falling sheet, while a slight decrease can break it into separate strands. This sensitivity is why waterfalls appear so different from week to week. Another often overlooked aspect is sound. The roar of peak runoff reflects not just volume, but turbulence. As flow increases, water collides with itself more frequently, converting motion into vibration. That vibration travels as sound, making spring runoff unmistakable even from a distance. As summer advances, rivers gradually lose this energy. Flow slows, channels narrow, and sound softens. By late summer, water systems enter a quieter phase. What remains is sustained by delayed snowmelt, shaded gullies, and slow groundwater release. Scientists describe this late-season flow as the memory of winter, a delayed response stored in snowpack and fractures. Through all of this, water continues to follow paths shaped by ice. It refines, redistributes, and repeats rather than reinventing. By the time autumn arrives, Yosemite's water systems have completed another cycle. Snow will soon begin accumulating again, restarting the process. The system does not reset, it layers. Each year adds subtle adjustments onto a framework set long ago. Water now governs daily change in Yosemite, setting the conditions that will soon shape soils, forests, and fire. Once water settled into seasonal rhythms, life responded. In Yosemite, forest did not appear all at once, but assembled gradually as soil formed and stabilized across the granite landscape. Soil is not simply dirt. It is a layered mixture of mineral particles, organic matter, water, air, and living organisms, built slowly from rock and life working together. In Yosemite, soil formation begins with granite breaking down. Physical weathering splits rock into smaller fragments, while chemical reactions alter minerals at the surface. Granite weathers slowly, which is why Yosemite soils are often thin and patchy. Where fractures are dense and water lingers, soil develops more readily. A useful way to picture this is to imagine soil as a savings account. Each year deposits are small, but over long periods, balance accumulates. Early soil contains little organic material. As plants establish, fallen needles, leaves, and roots add carbon, thickening the soil layer and improving its ability to hold water. One interesting fact is that a single centimeter of mountain soil can take hundreds of years to form. This slow pace means soil is easily lost and difficult to replace. Beneath the surface, fungi play a central role. Many Yosemite trees form partnerships with mycorrhizal fungi that connect roots to surrounding soil. These fungal networks act like extended plumbing systems. Fine threads spread far beyond root tips, increasing access to water and nutrients. In exchange, trees supply sugars produced during photosynthesis. Scientists describe this as a mutual relationship where both partners benefit. Research shows that connected fungi can transfer nutrients between trees of different ages and even different species. Older trees can support younger seedlings through these underground networks. This sharing helps stabilize forests during stress, such as drought. It also influences which species thrive in particular locations. Above ground, Yosemite forests organize themselves by elevation, moisture, and sunlight. Lower elevations support oak woodlands and mixed conifer forests. As elevation increases, species shift toward pine, fir, and eventually subalpine forests dominated by hardy conifers. Each tree species reflects specific adaptations. Thick bark protects some trees from heat, while narrow needles reduce water loss in dry conditions. Trees do not compete only vertically for light. They also compete below ground for water and nutrients, which shapes spacing and forest density. Forest structure develops in layers. Tall canopy trees capture most sunlight, while understory trees and shrubs occupy filtered light beneath. This layering affects temperature, humidity, and wind at ground level. In dense forests, shade reduces evaporation and slows soil drying. One interesting observation is that forests can modify their own climate. Shaded ground remains cooler, while transpiration from leaves adds moisture to the air. Fire is an essential part of this system. In Yosemite, fire has shaped forests for thousands of years. Before modern fire suppression, low-intensity fires burned frequently, often every 5 to 15 years in some forest types. These fires did not usually kill mature trees. Instead, they cleared accumulated needles, branches, and small seedlings from the forest floor. A useful analogy is sweeping a floor rather than burning a house. Frequent, low-intensity fire removes fuel, without destroying structure. Many Yosemite tree species evolved alongside fire. Thick bark insulates living tissue, while high branches keep flames away from crowns. Some pine species produce cones sealed with resin that only open when heated. Fire triggers seed release at a moment when competition is reduced. Fire also recycles nutrients. When organic matter burns, minerals locked in plant tissue return to the soil in readily available forms. Ash can temporarily increase soil fertility, promoting new growth. This pulse of nutrients supports grasses, shrubs, and seedlings after fire. Scientists note that fire creates diversity rather than uniformity. Burn severity varies across the landscape, producing a mosaic of conditions. Some patches burn lightly, others more intensely. This variation supports different species at different stages of recovery. Without fire, forests change in ways that increase risk. Fuel accumulates, tree density rises, and shade-tolerant species crowd out others. In these conditions, fires that do occur tend to burn hotter and more destructively. Evidence suggests many recent severe fires reflect this imbalance. Yosemite's fire management now aims to restore natural fire patterns. Prescribed burns are used to reduce fuel and reintroduce frequent, low-intensity fire. These practices are guided by decades of ecological research and historical records, including tree ring analysis that preserves evidence of past fires. Tree rings record not only age, but disturbance. Fire scars appear as darkened marks, allowing scientists to reconstruct fire frequency over centuries. After fire, regeneration begins quickly. Grasses and flowering plants often appear within the first growing season. Shrubs follow, stabilizing soil and providing shade for young trees. Over time, forests reassemble through predictable stages. This process is not a reset, but a continuation. Seeds stored in soil, roots that survived underground, and nearby trees all contribute. One interesting fact is that some fungi increase dramatically after fire, thriving on newly available organic material. These fungi support early plant growth. As forests recover, canopy gradually closes, shade increases, and conditions shift again. The system moves, but it does not repeat exactly. Each fire leaves a lasting imprint on structure and composition. Forests remember fire through spacing, age distribution, and species mix. In Yosemite, water, soil, fungi, trees, and fire form a tightly linked system. Changes in one affect all others. Snowmelt influences soil moisture. Soil supports roots and fungi. Vegetation shapes fuel availability. Fire resets structure and nutrient cycles. Scientists believe that Yosemite's forests were historically more open than many appear today, though the exact structure varied by elevation and exposure. This conclusion comes from tree ring records, early photographs, and charcoal layers preserved in soil. These records suggest frequent, low-intensity fires, limited tree density by selectively removing young growth. The mechanism is simple. Small trees and shrubs burn more easily, while thick-barked adults often survive. Yosemite begins to change when temperature patterns shift, rather than when rock moves. Scientists estimate that average temperatures in the Sierra Nevada have risen over the last century, based on long-term weather station records and tree ring data. Temperature matters because it controls how water enters the system. When air warms, the altitude at which snow can form rises, changing how winter precipitation is stored. Scientists believe more winter storms now deliver rain instead of snow at middle elevations, because freezing levels sit higher in the atmosphere. This conclusion comes from precipitation records showing declining snow water equivalent despite similar total precipitation. Snow stores water over time, while rain releases it immediately. A useful way to think about snowpack is as a savings account that releases water slowly instead of all at once. When snow melts earlier, river flow peaks earlier in the year. Stream gauge records show that peak runoff now arrives weeks sooner in warm years. Earlier runoff reduces late summer water availability. That matters because soils rely on stored moisture during the driest months. Soil holds water in tiny spaces between mineral grains and organic matter. When those spaces empty, microbial activity slows and nutrients become less available to plants. Trees respond to reduced soil moisture by closing leaf pores called stomata. This reduces water loss, but also limits carbon intake and slows growth. Scientists measure this stress through narrower annual growth rings during dry years. Reduced growth indicates less energy available for defense. Drought-stressed trees produce less resin. Resin requires water pressure to flow, and lower pressure weakens chemical defenses. This change affects insects next. Bark beetles locate stressed trees and bore through bark to reproduce. Scientists believe beetles succeed not because they increase in number, but because trees lose the ability to repel them. This is supported by outbreak timing that follows drought years. As trees die, canopy cover thins. More sunlight reaches the forest floor, increasing surface temperature. Warmer ground dries needles and small branches more quickly. Fuel moisture measurements show faster drying beneath open canopies. Dry fuels ignite more easily and spread fire faster. A useful analogy is dry paper compared with damp paper under the same flame. Wind amplifies this effect by supplying oxygen and pushing heat into unburned fuels. Observations show that wind-driven fires spread far faster than calm ones. Slope further accelerates spread. Flames tilt uphill, preheating vegetation above them. Humidity controls how quickly fine fuels dry. Low humidity allows grasses and needles to respond within hours. Lightning provides ignition at higher elevations. Scientists think dry lightning has become more consequential because fuels are now drier when storms occur. These processes reinforce one another. Earlier snowmelt dries soils, stressed trees thin canopies, and dry fuels carry fire more efficiently. Scientists believe threshold behavior emerges when these changes align. Evidence comes from years when modest warming produced outsized fire activity. The landscape remains stable in form, but sensitive in timing. When timing shifts, connected systems respond together. Earlier snowmelt alters meadows first. Meadows such as Tuolumne Meadows and Cook's Meadow rely on slow water release to keep soils saturated through summer. When meltwater arrives earlier, meadow soils dry sooner. Soil moisture probes show late-season water dropping weeks earlier in warm years, shortening the growing window. This drying shifts plant composition. Tall sedges in the genus Carex, with narrow blade-like leaves and dense root mats, decline first. Rushes in the genus Juncus, recognizable by their stiff, upright stems and preference for standing water, also lose ground. These plants require continuously wet soils to survive. Grasses such as Idaho fescue and needlegrass expand instead. These grasses have finer roots and tolerate drier soil, allowing them to spread as water retreats. A useful way to picture this shift is like changing flooring materials. Water-tolerant plants resemble tile in a wet room, while grasses behave more like wood that handles dryness better. Plant changes affect insects next. Meadow flowering shortens when water leaves early. Bumblebees such as Bombus vosnesensky are large and fuzzy, with black bodies marked by yellow bands. They emerge based on temperature, not soil moisture. Sulfur butterflies in the genus Coleus are pale yellow to white, fluttering low over grasses. Hoverflies in the genus Surface resemble small bees, but hover in place. When flowers fade before insects peak, food supply drops. This mismatch works like two conveyor belts running at different speeds, where items no longer meet at the transfer point. Insect numbers fall as a result. Grasshoppers in the genus Melanoplus, with elongated hind legs and mottled brown bodies, become less abundant. Moth caterpillars, soft-bodied and leaf-colored, decline as host plants dry. Ground beetles, dark and glossy with long legs, lose shelter as soil hardens. These insects support birds. Mountain bluebirds are small thrushes with bright blue backs and pale bellies, often seen perched on low shrubs. Violet-green swallows are slim birds with pointed wings and shimmering green and violet backs, catching insects in flight above meadows. Yellow-rumped warblers are small, streaked birds with flashes of yellow near the tail. All three feed insects directly to their nestlings. Bird chicks grow rapidly and require frequent feeding. When insects decline, parents return with smaller loads, similar to trying to stock a pantry with fewer deliveries. Aquatic insects link water timing to birds as well. American dippers are compact grey birds that bob constantly and walk underwater in cold streams. They feed on mayfly and caddisfly larvae that cling to submerged rocks. Earlier low flows reduce these larvae, shrinking the food supply. This is like lowering shelves in a warehouse, reducing how much inventory can be stored. Seed-eating birds respond too. Dark-eyed juncos are small grey birds with white outer tail feathers that flash during flight. White-crowned sparrows have bold black and white head stripes and forage along meadow edges. Shorter plant growth reduces seed production they depend on. Small mammals respond strongly. Belding's ground squirrels are tan, short-tailed rodents that sit upright near burrows, feeding on meadow plants. Golden-mantled ground squirrels resemble chipmunks, but lack facial stripes, with a golden stripe along the back. Both species rely on summer food to build fat. Fat storage works like charging a battery. An early dry season shortens the charging time before dormancy. Rodents that remain active year-round are also affected. Long-tailed voles have blunt snouts and thick grey fur, while deer mice have large eyes and white bellies. Reduced food lowers litter size and survival. Population trapping shows lower densities after dry summers. Predators follow prey availability. Great horned owls are large, mottled brown birds with prominent ear tufts and wide wings. Red-tailed hawks have broad wings and a brick red tail, often seen circling above open ground. When prey declines, predators range farther, increasing energy use like driving farther for the same groceries. Mammalian predators adjust as well. Coyotes are lean, long-legged canids with grey-brown coats and pointed muzzles. Bobcats are stocky with short tails and tufted ears, hunting quietly along meadow edges. Pine martens are slender, dark brown mammals with pale throats, moving through forest cover. Amphibians show rapid response. Sierra Nevada. Yellow-legged frogs are medium-sized frogs with mottled brown backs and yellow undersides. They breed in shallow ponds. Earlier drying strands tadpoles before metamorphosis, like draining a pool before swimmers reach the ladder. Reptiles balance heat and water. Western fence lizards have rough-scaled skin and blue patches on the belly, basking on rocks in spring. As heat increases, they retreat into shade to avoid dehydration, similar to stepping indoors during peak heat. Sierra Nevada alligator lizards are long-bodied with smooth, shiny scales and foldable skin along the sides, hiding under logs. Common garter snakes are slender, with yellow stripes along dark bodies, often near water. When moist refuges dry, feeding time decreases. At lower elevations, northern Pacific rattlesnakes are thick-bodied with diamond patterns and a rattle at the tail, active during warm periods but avoiding extreme heat. Higher elevations face different constraints. Lodgepole pine has thin bark and narrow needles. Red fir grows tall with smooth grey bark, and white bark pine has clustered needles and twisted forms. Snow insulates their roots. Snow acts like a thermal blanket. When snow melts early, roots experience freeze damage. Trees divert energy into repair instead of cone production. Whitebark pine depends on Clark's nutcrackers. These birds are grey with black wings and strong bills, caching seeds in soil. Those caches act like seed banks. When cone crops fail, fewer caches mean fewer seedlings later. Fire overlays these effects. Burned soil darkens and absorbs more sunlight, drying faster like dark pavement compared with grass. Seedlings of ponderosa pine and incense cedar fail more often under early drying. Shrubs such as manzanita with smooth red bark and ceanothus with glossy leaves expand. Shrub fuels connect across the ground, like laying a continuous line of kindling. Not all areas respond equally. North-facing slopes and wet seeps retain moisture longer. These areas act as refuges. Species persist there when surrounding areas become stressful. Yosemite's connected terrain allows movement. Mule deer with tan coats and large ears move upslope, and black bears with thick dark fur shift feeding areas. Connectivity works like a pressure release valve, preventing stress from concentrating. Physiology sets limits. Repeated dry years exhaust reserves. Timing remains the driver. Snow shapes water, water shapes plants, plants shape insects, insects shape birds and mammals. Each step hands influence forward. The landscape continues adjusting rather than reaching an endpoint. As temperatures rise, changes in precipitation do not occur evenly across Yosemite. Elevation determines where snow persists and where rain becomes dominant. Scientists estimate that the strongest shift from snow to rain occurs between 1,500 and 2,500 meters. This conclusion comes from long-term snow course measurements showing declining snow water equivalent at these elevations. This elevation band matters because it historically stored delayed water for both forests and meadows. When storage shrinks here, water moves through the system earlier and faster. Rain behaves differently than snow because it does not pause in place. Rain moves immediately downhill under gravity, while snow holds water until temperatures rise. A useful way to picture this difference is a conveyor belt compared with a shelf. Rain stays on the belt and keeps moving, while snow waits on the shelf until release. When more winter precipitation falls as rain, streams rise quickly during storms. Stream gauge records show sharper peaks, followed by faster declines. These rapid rises increase erosion because faster water carries more energy. That energy allows sediment to be lifted and moved more efficiently. Aquatic insects respond first because they live directly in the flow. Mayfly larvae with flattened bodies cling to rocks, while caddisfly larvae build protective cases from sand and plant fragments. Repeated surges dislodge these larvae from their anchors. Sampling after rain-dominated winters shows reduced insect density. Aquatic insects form the base of cold water food webs. When larvae decline, less energy moves upward into fish. Rainbow trout have silver bodies with a faint pink stripe along the side. Juveniles depend on drifting insects to grow during short summer windows. Reduced insect availability slows trout growth. Smaller fish enter winter with fewer energy reserves. Energy storage in fish works like a fuel tank. When the tank is not filled during summer, survival margins narrow during winter. Birds that hunt fish respond next. Ospreys with white heads and dark eye stripes rely on clear water where prey is visible. When fish are smaller or less abundant, ospreys spend more time hunting. Increased effort reduces nesting success. Streamside vegetation changes as well. Faster flows erode undercut banks once stabilized by willows. Willows have narrow leaves and flexible branches that anchor soil and shade water. When roots are exposed, trees topple and shade is lost. Loss of shade allows sunlight to warm stream water. Warmer water holds less dissolved oxygen. Lower oxygen stresses cold water species. Trout respiration becomes less efficient as temperatures rise. Amphibians respond differently because their life cycles depend on shallow water. Pacific tree frogs are small with smooth green or brown skin and wide toe pads. They breed in quiet pools along stream margins. Rapid flow washes eggs downstream or drains pools before development completes. Reptiles shift behavior rather than disappearing. Western terrestrial garter snakes have slender bodies with yellow stripes along dark scales. When banks collapse and vegetation thins, shelter declines. Snakes retreat upslope into rock crevices and dense cover. Upland soils experience heavy rainfall differently than snowmelt. Water runs off compacted or dry soil instead of soaking in. This behaves like pouring water onto hard clay rather than loose soil. Infiltration decreases and recharge weakens. Reduced recharge affects springs later in summer. Plants that rely on seepage lose habitat as flows diminish. Shooting stars and elephant head flowers decline where moisture disappears early. Pollinators shift with them. Bumblebees with thick fuzzy bodies and long tongues follow remaining nectar sources. Foraging routes lengthen as resources fragment. Small mammals respond next. Douglas squirrels with gray-brown fur and bushy tails rely on conifer cones for energy. Cone development depends on water timing from previous years. Drought reduces cone size and number. Reduced cones affect seed dispersers. Clark's nutcrackers cache pine seeds in soil. These caches act like seed banks. Fewer caches mean fewer seedlings in later years. Forest structure changes slowly as regeneration falters. Gaps widen and sunlight reaches the forest floor. Increased sunlight dries needle litter earlier in summer. Fuel moisture drops. Fire ignition becomes easier under these conditions. Fine fuels ignite with less heat. Rain-dominated winters followed by dry summers increase fire likelihood. Early growth is later cured. This sequence works like growing grass and letting it dry completely. Fuel accumulates and becomes ready to burn. Large herbivores respond to changing forage. Mule deer with tan coats and large ears browse earlier in spring. Earlier browsing reduces recovery time. Meadows thin faster under repeated pressure. Predators track prey movement. Mountain lions with tawny coats and long tails follow deer into new areas. Nothing in this sequence acts alone. Water timing shapes streams. Streams shape insects, Insects shape fish, and fish shape birds. Vegetation shapes fire, and animals redistribute pressure. Each step hands influence forward. The system continues adjusting as precipitation patterns vary year to year. Timing remains the controlling factor. Changes in water timing also affect lakes, especially shallow alpine basins. When ice leaves earlier, lake water warms sooner in spring. Warmer water increases biological activity. Plankton populations grow faster as temperature rises. Zooplankton such as Daphnia, small transparent crustaceans that move with beating antennae, feed on algae near the surface. Their growth depends on both temperature and nutrient availability. When plankton blooms occur earlier, food availability for fish larvae shifts. Survival depends on whether larvae hatch when prey is abundant. This timing mismatch works like opening a cafeteria before students arrive. Food exists, but the benefit is missed. Birds that rely on lakes respond next. Common mergansers, long-bodied ducks with narrow red bills, feed on small fish in clear water. Earlier warming can increase early season feeding. Later in summer, reduced fish size limits energy return. Wetland edges change as waterlines retreat. Cattails and sedges thin as soils dry. Marsh wrens, small brown birds with bold white eyebrow stripes, lose nesting cover when stems decline. Reduced cover increases exposure to predators. Insects shift again. Dragonflies, with long slender bodies and clear wings, depend on standing water for larval development. Earlier drying shortens larval growth. Fewer adults emerge later in the season. Bats respond to insect availability. Little brown bats, small dark furred mammals with short ears, hunt insects over water and meadows. Reduced insect swarms require longer hunting time. Energy balance tightens during warm, dry periods. This is like driving farther for the same groceries. Effort increases while return stays limited. Plants near streams feel repeated stress. Cottonwoods with broad leaves rely on consistent groundwater access. When water tables drop early, seedling roots fail to reach moisture. Recruitment declines. Over time, stream corridors narrow and lose shade. Warmer water conditions reinforce earlier changes. These effects accumulate rather than reset. Each year adds adjustment on top of the last. The system remains connected. Timing continues to shape outcomes across water, plants, and animals. As temperatures rise, biological stress is driven less by gradual warming and more by short periods of extreme heat. These heat events matter because living systems respond strongly to brief overloads rather than slow averages. During heat waves, soil and exposed granite surfaces absorb large amounts of energy during the day and release it slowly overnight. This keeps nighttime temperatures elevated, reducing the cooling period organisms rely on to recover. Plants are affected first through respiration. When nights stay warm, plants continue to burn stored sugars, while photosynthesis pauses, draining energy reserves. This imbalance works like running appliances overnight without refilling the power supply during the day. Energy stores shrink even if daylight conditions seem manageable. Shallow-rooted plants respond earliest. Meadow wildflowers such as alpine buttercups and shooting stars wilt sooner when repeated heat prevents overnight recovery. Woody shrubs respond differently. Manzanita with smooth red bark and small leathery leaves retain water more efficiently and tolerate heat better than herbaceous plants. As shrubs expand, they shade out low-growing flowers and grasses. This shifts plant diversity and alters food availability for insects. Insects respond quickly because their body temperature matches air temperature. Grasshoppers in the genus Melanoplus become active earlier in the day, but retreat sooner as heat intensifies. Higher activity raises feeding rate, but also increases water loss. During extreme heat, total energy intake often declines rather than increases. Butterflies show a similar pattern. Sulfur butterflies in the genus Coleus fly during cooler morning hours and shelter by midday, shortening mating and feeding windows. This timing shift reduces reproductive success even when food plants are present. Activity time matters as much as resource availability. Beetles respond through behavior rather than movement. Darkling beetles with hard black bodies shelter beneath soil and litter, reducing heat exposure but limiting feeding. Birds adjust daily schedules next. Mountain chickadees with graybacks and black caps forage intensively at dawn before retreating to shade. Reduced foraging time affects nestlings. Parents make fewer feeding trips during heat, slowing chick growth. This functions like shortening delivery hours to a store, while demand remains high. Supply fails to meet needs. Larger birds manage heat differently. Common ravens with glossy black feathers cool themselves by panting, which increases water loss during prolonged heat. Dehydration risk rises when water sources are limited. Energy is diverted from feeding to cooling. Mammals shift behavior rather than physiology. Mule deer with tan coats rest in shaded forest patches during midday and feed during cooler hours. When nights remain warm, total feeding time shrinks. Energy intake drops despite behavioral adjustment. Small mammals face stricter limits. Pikas with dense fur and rounded ears overheat easily and depend on cool air trapped in talus slopes. When heat penetrates these rock spaces, refuge disappears. Survival becomes dependent on short, cool intervals. Reptiles tolerate heat, but still face thresholds. Western fence lizards bask to warm, but retreat when body temperature exceeds safe limits. Heat speeds digestion, but increases dehydration risk. Activity windows narrow during prolonged heat. Snakes respond through shelter selection. Northern Pacific rattlesnakes remain in rock crevices during peak heat, reducing hunting opportunities. Heat also accelerates decomposition. Soil microbes break down organic matter faster under warm conditions, releasing nutrients rapidly. This process resembles compost heating up. Material breaks down quickly, but does not last as long. Rapid decomposition reduces long-term soil carbon and moisture retention. Drier soils heat more easily, reinforcing surface warming. Fire conditions respond directly. Fine fuels dry rapidly during heat waves, lowering ignition thresholds. Animals respond to smoke as well as heat. Black bears with thick, dark fur move toward water or higher elevations during smoky periods. Birds abandon nests when smoke persists. Nest failure increases even without direct fire damage. Water systems are affected next. Streams warm during heat events, reducing dissolved oxygen. Aquatic insects drift downstream, seeking cooler refuges. Fish concentrate in deep shaded pools. Crowding increases competition. Stress rises as usable habitat shrinks. Extreme heat compresses life into fewer safe spaces. Refuges become crowded, and recovery slows. As heat events occur more often, systems have less time to reset. Resilience depends on timing rather than average conditions. The landscape continues adjusting through behavior, physiology, and movement. Extreme events now shape outcomes as strongly as gradual change. Heat also changes how animals use water sources across the landscape. During prolonged hot periods, creeks, seeps, and springs become centers of activity, rather than just passageways. Mule deer with tan coats and large dark eyes gather near shaded stream bends where temperatures remain lower. This concentration increases grazing pressure on nearby grasses and shrubs. Plants along these corridors experience repeated browsing. Recovery slows because regrowth occurs during the hottest part of the season. Small mammals respond by clustering near moisture. Deer mice with large eyes and white bellies forage along damp edges where seeds persist longer. Higher density increases competition. Some individuals are forced into drier habitat where survival drops. Predators adjust quickly to this compression. Coyotes with gray-brown fur and narrow muzzles patrol water corridors more frequently during heat waves. This concentrates hunting pressure along limited paths. Prey experience higher mortality, even without increases in predator numbers. Birds show similar compression around water. California quail with rounded bodies and forward-curving head plumes gather in shaded riparian zones. Increased grouping raises disease and parasite transmission. Close roosting allows mites and lice to spread more easily. Heat also affects the timing of reproduction. Many species rely on temperature cues to initiate breeding cycles. When heat arrives early, breeding may begin before food peaks. Juveniles then hatch into conditions that cannot support rapid growth. This timing mismatch works like starting a factory shift before raw materials arrive. Activity begins, but output fails. Some insects gain advantage under heat. Ant species with dark, glossy bodies forage actively when competitors retreat. Increased ant activity alters seed dispersal. Ants remove and relocate seeds more frequently, changing where plants establish. Certain plants rely on ants to carry seeds away from parent plants. When ant behavior shifts, plant spacing changes across the meadow. Lizards exploit temporary insect abundance. Western fence lizards with rough scales and blue belly patches feed heavily early in the day. As temperatures rise further, dehydration risk increases. Activity windows shrink again despite food availability. Snakes adjust hunting timing instead of location. Gopher snakes with tan and brown blotched patterns hunt during cooler mornings. Shorter hunting periods reduce intake. Juvenile growth slows under repeated heat stress. Heat also affects egg development. Reptile eggs incubate in soil where temperature controls development speed. Warmer soil accelerates development but increases mortality. Hatchlings emerge smaller and less robust. This process is like cooking food faster at higher heat. Speed increases, but quality declines. Bird eggs face similar stress. Exposed nests heat quickly when shade is reduced. Parent birds shade eggs by standing over them. This reduces feeding time and increases adult energy loss. Extended heat forces trade-offs. Adults balance cooling eggs against finding food. Heat alters sound transmission as well. Warm air changes how sound travels across open ground. Bird calls carry differently at dawn than midday. Communication ranges shrink during extreme heat. Territorial defense weakens as calls travel shorter distances. Boundaries blur between neighboring birds. Mammals that rely on scent also face changes. Heat accelerates scent breakdown in soil and vegetation. Chemical signals fade faster. Territory marking requires more frequent renewal. This increases energy use without increasing resources. Maintenance costs rise across individuals. Plants experience structural stress under heat. Leaves lose water faster than roots can replace it. Stomata remain closed longer. Carbon intake drops and growth slows. Heat affects underground partners as well. Mycorrhizal fungi rely on moist soil to transport nutrients. Dry soil breaks fungal connections. Trees lose access to distant water and minerals. This disconnect works like severing underground cables. Supply lines fail even if the source remains intact. Fire risk escalates further under prolonged heat. Larger fuels such as branches and logs dry more thoroughly. These fuels normally resist ignition. Under extreme heat, they become receptive. This extends the fire season. Windows of risk widen on both ends. Animals often detect fire conditions early. Birds flush from areas before smoke appears. Mammals alter movement patterns days in advance. Stress hormones increase even without flames. Even without fire, heat reshapes behavior. Energy budgets tighten across species. Some individuals survive by moving. Others survive by reducing activity. Those unable to do either face higher mortality. Selection pressure increases. Over time, heat favors traits that conserve water and tolerate stress. Population composition shifts gradually. These shifts occur unevenly across terrain. Microhabitats buffer some species. North-facing slopes, talus fields, and deep shade retain cooler conditions. These places function as thermal refuges. Refuges operate like cooling rooms during a heat wave. Access determines survival. As heat events repeat, dependence on refuges increases. Crowding intensifies within limited space. Competition within refuges grows. Benefits diminish as density rises. The system continues adjusting through redistribution rather than collapse. Stress spreads across space instead of concentrating instantly. Extreme heat reshapes patterns rather than removing life outright. Timing and access determine outcomes. The landscape remains active. Responses layer on top of earlier changes. Changes in heat and water timing reshape forests through stress long before widespread tree death appears. Trees respond first through internal physiology rather than visible collapse. When temperatures remain high and soil moisture drops, trees reduce water loss by closing stomata on their needles or leaves. This protects internal tissues, but also limits carbon intake, slowing growth and energy production. Reduced growth is measurable in tree rings. Studies show narrower annual rings during consecutive warm, dry years, indicating less energy available for maintenance and defense. Different tree species respond unevenly. Ponderosa pine with thick bark and long needles tolerates drought better than lodgepole pine, which has thinner bark and shallower roots. Shallow-rooted trees draw water from upper soil layers. When those layers dry early, stress develops sooner and lasts longer. This stress weakens internal transport systems. Water normally moves upward through trees by pressure differences created as moisture evaporates from leaves, and reduced soil moisture disrupts that flow. The process works like drawing liquid through a straw. When liquid becomes scarce, air enters and movement fails. Disrupted water flow limits resin production. Resin depends on water pressure to move through ducts and seal wounds. In drought-stressed trees, resin pressure drops. This reduces the ability to repel invading insects. Bark beetles exploit this weakness. Mountain pine beetles are small cylindrical insects with dark brown bodies that bore through bark to lay eggs. As beetles tunnel, they introduce fungi that block water transport inside the tree. This compounds stress and accelerates mortality. Outbreaks follow drought patterns rather than single hot years. Beetle success rises after several consecutive warm, dry seasons. As trees die gradually, forest structure shifts. Canopy gaps widen, and sunlight penetrates deeper into the forest. Increased light warms the forest floor. Needle litter dries earlier and remains dry longer. This alters understory vegetation. Shade-tolerant plants decline, while sun-tolerant shrubs expand. Manzanita with smooth red bark and stiff evergreen leaves spreads efficiently in open light. Ceanothus with glossy leaves and deep roots also gains advantage under drier conditions. Shrub dominance changes fuel structure. Fine fuels connect more continuously across the ground. This connection behaves like linking individual matches into a single line. Fire can move without interruption. Trees that survive face new stresses. Increased wind exposure raises evaporation from needles and branches. Higher wind dries foliage faster. Heat-driven water loss compounds. Birds that depend on forest cover respond. Hermit thrushes with brown backs and spotted breasts nest in shaded understory. As canopy thins, nests become more exposed. Predation risk increases and nesting success declines. Other birds respond differently. Hairy woodpeckers with black and white plumage and long bills exploit dead trees for insects. An increase in standing dead trees creates temporary feeding opportunities. This short-term benefit does not last. As snags fall and decay, food availability shifts again. Species composition continues to change. Mammals respond to altered structure. Pine martens with dark brown fur and pale throats rely on dense cover to hunt effectively. As cover thins, hunting efficiency drops. Martens shift toward remaining dense patches. Larger mammals respond through movement. Black bears with thick dark fur forage in open areas, but rely on forest cover for travel. Fragmented cover increases energy costs. Travel routes become less efficient and riskier. Forest floor organisms respond as well. Mycorrhizal fungi depend on moist soil to maintain networks that transport nutrients. Dry soil breaks fungal connections. Nutrient flow to tree roots declines. This disruption works like cutting underground supply lines. Resources exist, but cannot reach where they are needed. Tree seedlings are especially vulnerable. Their shallow roots cannot access deeper moisture during drought. Seedling mortality rises during hot, dry summers. Regeneration slows across large areas. Without consistent regeneration, forest age structure shifts. Older trees dominate, while younger cohorts thin. This reduces long-term resilience. Diversity declines over time. Fire interacts strongly with these changes. Shrub-dominated understories carry flames upward into tree crowns. Crown fires differ from surface fires. They kill entire trees rather than thinning understory growth. Animals respond differently to burned forest. Mule deer with tan coats browse on fresh shoots after fire. Predators follow prey into burn edges. Mountain lions with tawny coats hunt along these transition zones. Birds recolonize at different rates. Black-backed woodpeckers with black plumage and white wing patches specialize in burned forests. They feed on beetle larvae in fire-killed trees. This creates a short-lived food pulse. As snags decay, that pulse fades. Species composition shifts again. Forest recovery depends on water timing. Seedlings require moisture during early growth stages. When water leaves early, recovery slows. Open conditions persist longer. This extends the window for repeated fire. Feedbacks strengthen over time. Not all forest areas respond equally. North-facing slopes retain moisture longer and buffer heat stress. These areas act as refuges. Species persist there while surrounding forests change. Refuges function like storage rooms during a heat wave. They preserve options when conditions worsen. As heat and drought repeat, dependence on refuges increases. Competition within them intensifies. Over longer spans of time, Yosemite responds to accumulated change rather than single events. Small seasonal shifts add up, gradually reshaping how water, soil, plants, and animals occupy the landscape. One of the strongest long-term drivers is snow reliability. Scientists estimate that the average elevation where snow persists through winter has moved upslope by several hundred meters over the past century, based on snow course records and temperature trends. As snow reliability shifts upward, the area receiving delayed water shrinks. This matters because delayed melt controls how long soils remain moist and how steadily streams flow through summer. Snow that melts early behaves differently from snow that melts late. Early melt sends water downstream before plants are actively growing, leaving less available later when demand is highest. A useful way to think about this is like watering a garden before seeds sprout. The water is real, but the timing limits how much benefit plants can extract. Earlier high flows also change how sediment moves. Streams carry sand, gravel, and silt downstream before roots can stabilize banks. This reshapes channels over time. Research shows that streams experiencing earlier peak flows tend to widen and become shallower. Shallow channels warm faster because more water is exposed to sunlight. Warmer water holds less dissolved oxygen, which stresses aquatic organisms. Fish respond by concentrating in the coldest remaining reaches. Brook trout and rainbow trout depend on shaded pools and groundwater-fed sections to survive late summer. As these refuges shrink, competition increases. Growth slows and disease spreads more easily in crowded conditions. Over years, populations adjust through selective survival. Individuals that tolerate warmer, lower oxygen water persist more often. Plant communities respond through recruitment rather than collapse. Seedlings that require long moist periods simply fail to establish during dry years. This process is slow but decisive. Mature trees remain while the next generation quietly shifts in composition. Scientists often describe this as lagged change. It is similar to replacing components in a machine only when old parts finally wear out. Fire frequency also influences long-term structure. Charcoal layers in sediment cores and fire scars in tree rings show how often fires burned historically. When fires return more frequently than forests can rebuild, structure simplifies. Trees that require decades to mature are replaced by shrubs that grow and reproduce quickly. Shrubs store less carbon in wood. Energy shifts from long-term storage to fast turnover. Fast turnover increases fine fuels. Fine fuels dry quickly and carry fire easily. This creates a feedback. Fire promotes vegetation that makes future fire more likely. Animals respond to these gradual changes by adjusting habitat use. Species that depend on dense forest retreat into remaining patches. Others expand into open ground. Generalist species replace specialists. This reduces ecological diversity over time. Fewer habitat types support fewer specialized relationships. Soils respond as well. Repeated heating and drying reduce organic matter accumulation. Organic matter acts like a sponge. When it declines, soils lose water holding capacity and heat faster. This loss feeds back into plant stress. Roots encounter dry conditions earlier each growing season. Nutrient cycling also changes. Microbial activity shifts from steady processing to brief pulses after moisture events. Plants adapted to rapid uptake benefit. Slow-growing species lose access to nutrients. These changes accumulate gradually. Each year adds a small adjustment rather than resetting conditions. Scientists studying long-term plots observe reorganization rather than collapse. Systems settle into new configurations constrained by timing. The granite foundation remains unchanged. What changes is how living systems occupy that foundation. Elevation continues to provide variation. Higher zones retain colder conditions and later snowmelt. These zones function as long-term reservoirs of diversity. They slow change by preserving cooler microclimates. Connectivity across elevations becomes increasingly important. Movement allows species to track suitable conditions across generations. When movement pathways remain intact, populations adjust gradually. When pathways break, local loss accelerates. Time integrates all of these effects. Short-term stress becomes long-term structure. The landscape moves forward, shaped by accumulation rather than sudden events. What persists reflects decades of layered change. Snow persistence also controls how deep water penetrates the ground. Scientists observe that slow melt allows water to soak into fractures and soil layers rather than rushing away at the surface. When melt is gradual, groundwater recharge improves. This matters because groundwater feeds springs and cold stream reaches long after surface flow declines. Groundwater movement is slow by comparison. Tracer studies show that water entering fractured granite can take months to years to reappear downslope. This delay acts like a savings account with a long waiting period. The benefit arrives later, but only if deposits were made slowly enough to be retained. As snow lines rise, fewer areas contribute to this slow recharge. More water exits the system quickly, reducing the buffer that once smoothed dry seasons. Streams respond by becoming more variable. Peak flows arrive earlier, and low flows deepen later in summer. This variability changes habitat stability. Organisms adapted to steady conditions lose ground. Stoneflies and mayflies that require cold, consistent flow decline first. Their larvae cannot tolerate repeated warming and drying. Their loss alters food quality. Fish lose access to high-energy prey and shift diets. Rainbow trout compensate by feeding more on midges and small crustaceans. Growth slows because these foods provide less energy per capture. This shift resembles switching from dense bread to watery soup. Volume may remain, but nourishment declines. Plant roots also respond to changing moisture timing. Fine roots that absorb water are concentrated near the soil surface. When surface layers dry earlier, roots die back. Plants must regrow them each year, increasing energy cost. Repeated root loss weakens plants over time. Growth becomes increasingly limited even in average years. Tree species differ in their ability to cope. Ponderosa pine with deep root systems persist longer than species relying on shallow moisture. As deep-rooted species gain advantage, forest composition shifts subtly. The canopy changes without dramatic die-off. This gradual replacement is easy to miss. It works like changing the ingredients in a recipe one at a time. Soils record these changes as well. Reduced organic input slows soil building. Thinner soils hold less water and nutrients. Heat penetrates deeper and dries them faster. This feeds back into plant stress. Each season begins with less stored moisture than the last. Fire frequency intersects with this trend. Shorter intervals between fires interrupt soil recovery. Charcoal layers show that repeated burns reduce organic horizons. Nutrients are lost faster than they are replaced. This loss limits seedling establishment. Bare mineral soil dominates larger areas. Shrubs that resprout quickly gain advantage. Trees that rely on seeds lose ground. Animals respond to these structural shifts. Species that nest or forage in dense cover retreat. Generalist species increase in relative abundance. Diversity declines through replacement rather than disappearance. Elevation gradients still provide contrast. Higher slopes retain snow later and release water more slowly. These areas function as climate refuges. They preserve conditions that have vanished elsewhere. Refuges are unevenly distributed. North-facing slopes and shaded basins offer the strongest buffering. Access to refuges determines persistence. Species with mobility adjust more easily than those tied to fixed sites. This difference becomes apparent over generations. Reproductive success varies based on access rather than tolerance. Scientists studying long-term plots observe these patterns clearly. Change appears patchy rather than uniform. Patchiness reflects local conditions. Moisture, shade, and soil depth create varied outcomes. This mosaic slows system-wide collapse. It spreads stress across space. However, patchiness also complicates recovery. Some areas rebound while others continue to degrade. Time integrates these effects. Short-term extremes become long-term structure. The landscape records this integration silently. Forests, streams, and soils reflect accumulated history rather than single events. Over decades, Yosemite shifts toward configurations shaped by timing. What persists is what aligns best with new schedules of water and heat. The process is steady rather than dramatic. Change advances through repetition. Each year adds another layer. The result is a landscape that looks familiar, but functions differently. As time extends further, chemical processes begin to matter as much as physical ones. Temperature and moisture together control how elements move through soils, water, and living tissue. One important process is weathering of granite into mineral particles. Scientists observe that warmer and wetter conditions speed chemical reactions that break feldspar into clay minerals. Clay formation changes soil texture. Clay particles are smaller and hold water more tightly than sand-sized grains. This matters because water held tightly is less available to roots. Plants may experience water stress even when soil appears moist. A useful way to think about this is money locked in a long-term account. The funds exist, but access is limited when needed quickly. Chemical weathering also releases nutrients. Potassium and calcium freed from minerals enter soil solution. These nutrients support plant growth. However, their availability depends on timing and root activity. When release occurs outside the growing season, nutrients wash away. Streams carry them downstream before plants can absorb them. This loss reduces fertility over time. Soils gradually become less productive. Scientists studying long-term plots in granitic landscapes observe this slow decline. Nutrient budgets shift without dramatic visual change. Nitrogen cycling also changes. Warmer soils increase microbial conversion of organic nitrogen into forms plants can use. This process accelerates during brief wet periods. Pulses of nitrogen appear after storms or snowmelt. Plants adapted to rapid uptake benefit. Others miss the window and fall behind. This dynamic resembles a delivery truck arriving unexpectedly. Only those present can unload supplies. Streams respond chemically as well. Higher nutrient pulses increase algal growth on rocks. Algae form thin films called biofilms. These films change how insects graze and how oxygen moves across surfaces. Mayfly and caddisfly larvae feed on biofilms. Changes in biofilm composition alter their growth rates. Faster-growing larvae emerge earlier. Timing of emergence shifts relative to predators. Birds feeding on aquatic insects must adjust. Mismatches reduce feeding efficiency during breeding. Water chemistry also affects metal mobility. Iron and manganese dissolve more readily under warm, low oxygen conditions. These metals stain stream beds and clog gills of some organisms. Sensitive species decline first. Fish respond behaviorally. Trout avoid reaches where chemistry fluctuates strongly. Avoidance concentrates fish elsewhere. Competition intensifies in remaining suitable habitat. Lakes show similar chemical shifts. Warmer surface water increases stratification duration. Stratification separates oxygen-rich surface water from deeper layers. Oxygen depletion develops at depth. Cold-adapted organisms retreat upward. Habitat volume shrinks vertically. This is like lowering a ceiling in a room. Usable space decreases without walls moving. Decomposition also responds to chemistry. Microbes break down leaf litter faster when temperatures rise. Faster decomposition releases carbon dioxide. Soil carbon storage declines. Lower carbon reduces soil structure. Aggregates break apart more easily. Water infiltration decreases as structure weakens. Runoff increases during storms. This feeds back into erosion. Fine particles wash into streams. Sediment clouds water. Light penetration drops. Reduced light limits. Photosynthesis. Aquatic plants and algae adjust downward. Energy flow through the system declines. Less energy enters food webs. Terrestrial plants respond to nutrient loss by reallocating growth. Leaves become smaller and tougher. Tougher leaves deter herbivores. Insects feeding on foliage grow more slowly. Slower insect growth reduces prey quality. Predators expend more effort per calorie. This resembles eating low-density food. Volume increases while nourishment falls. Animals adjust through diet shifts. Generalists replace specialists. Specialist relationships weaken. Ecological networks simplify. Soil fungi respond as well. Mycorrhizal associations change with nutrient availability. When nutrients are scarce, fungi demand more carbon from plants. This increases plant energy cost. Plants under stress reduce carbon supply. Fungal networks shrink. Shrinking networks reduce nutrient access further. Feedback strengthens limitation. Over decades, these chemical shifts accumulate. The landscape transitions toward lower fertility states. Scientists call this progressive nutrient limitation. Evidence comes from long-term experiments in warming forests. The granite base remains constant. Chemistry alters how life interacts with that base. Elevation again moderates change. Higher zones remain cooler and chemically slower. These areas preserve older nutrient cycles. They act as reference conditions. Lower elevations diverge first. Differences widen across the gradient. Connectivity does not move chemistry. Species must adapt locally or relocate. Relocation carries cost. Energy spent moving reduces reproduction. Chemical changes therefore influence distribution indirectly. Fitness varies by location. Time integrates these processes quietly. No single year defines the outcome. Instead, patterns emerge from repetition. Each season nudges the system. The result is a landscape still recognizable in form. its internal functioning shifts beneath the surface. Understanding these changes requires patience. Chemistry moves slower than fire or flood, yet its influence is persistent. It shapes limits that other processes cannot cross. As chemistry sets new constraints, biological strategies adjust. What survives aligns with altered cycles. The landscape continues forward, shaped by reactions as much as by forces. What remains reflects long interaction between rock, water, and life. As chemical constraints deepen, feedbacks between soil and water intensify. Small shifts in pH and oxygen availability change, which reactions proceed efficiently. Warmer soils often become slightly more acidic as organic acids accumulate. This acidity increases mineral dissolution, but also mobilizes elements plants cannot easily use. Aluminium becomes more available under these conditions. Roots encountering dissolved aluminium grow more slowly and branch less. Reduced root growth limits exploration of soil. Plants access a smaller volume of water and nutrients. This is similar to narrowing the aisles in a warehouse. Supplies may exist, but reach becomes restricted. Streams reflect these soil changes. Increased acidity alters how phosphorus binds to sediments. When phosphorus binds tightly, algae receive less of it. Primary production declines even when light and water remain adequate. Lower production reduces insect grazing pressure. Insect populations thin without dramatic die-offs. Fish respond indirectly. Reduced insect drift lowers feeding efficiency over the season. Lakes show parallel effects. Extended stratification limits mixing of nutrients from deeper layers. Surface waters become nutrient poor. Algal communities shift towards species tolerant of scarcity. These species grow slowly. Food webs lengthen and lose efficiency. This resembles replacing fast supply chains with slower ones. Delays compound through the system. On land, leaf litter chemistry changes. Tougher leaves decompose slowly and accumulate. Accumulated litter insulates soil. Temperature fluctuations dampen near the surface. Dampened fluctuation slows microbial bursts. Nutrient pulses weaken. Plants adapted to steady supply lose advantage. Opportunists dominate brief pulses. Fungi alter enzyme production accordingly. Energy investment shifts toward survival rather than expansion. Reduced fungal reach limits plant access. Mutual benefits decline. Across decades, these interactions stabilize at lower throughput. Energy flow narrows. Narrower flow constrains population sizes. Carrying capacity declines gradually. Species distributions adjust along the gradient. Lower elevations show earlier change. Higher elevations lag behind. Chemical clocks tick slower in cold conditions. This delay creates contrast. Diversity persists longer in cooler zones. As gradients steepen, boundaries sharpen. Transitional zones compress. Compression increases competition. Edges become crowded. Crowding raises sensitivity to disturbance. Small shocks have larger effects. Over time, chemistry sets the background rules. Physical events play out within those rules. The landscape remains familiar in outline. Its internal exchanges operate differently. These differences accumulate without spectacle. Change proceeds through countless reactions. What persists aligns with altered chemistry. Limits become the new normal. The system continues forward constrained yet active. Interaction replaces abundance as the defining feature. Over long periods, adaptation operates through small differences in survival that repeat across many seasons. Those differences accumulate quietly, reshaping populations without dramatic events. One major pressure involves water use in plants growing on exposed slopes and valley rims. Scientists measure this using leaf gas exchange and carbon isotope ratios that reveal how tightly plants regulate water loss. Water loss occurs through transpiration, when moisture exits through stomata in leaves or needles. When dry air pulls water out faster than roots can replace it, internal pressure drops and tissues lose function. Plants that restrict transpiration maintain pressure longer. This allows photosynthesis to continue later into dry periods. A useful way to picture this is a faucet turned partway down. Flow continues, but the supply lasts longer under limited conditions. Needle structure plays a role in this control. Ponderosa pine needles have waxy coatings and sunken stomata that reduce evaporation during hot afternoons. These traits slow growth during wet years. They act like insulation during dry years, preventing catastrophic failure. Hydraulic failure occurs when air bubbles form inside water carrying tissues. Once bubbles expand, water transport can break down completely. This transport system functions like a drinking straw. If air enters the straw, liquid flow stops, even if water remains below. Selection becomes visible during seedling establishment. If several dry summers occur in sequence, seedlings lacking these traits fail to survive. This shifts forest composition without obvious die-off. The next generation simply differs from the last. Animals face similar pressures through water balance and heat load. Individuals that conserve water and avoid peak heat persist more often. Mule deer reduce heat stress by feeding at dawn and dusk and resting during midday. This lowers water loss from breathing and reduces overheating. That adjustment works like shifting work hours to early morning. The same tasks cost less energy. Black bears also shift timing and routes. During hot or smoky periods, they concentrate movement near water and shaded travel corridors. This concentrates activity into fewer paths. Energy is spent navigating stress rather than gaining calories. Birds show adaptation through timing of reproduction. When insect peaks shift earlier, birds that nest earlier raise more young. Wilson's warblers and yellow-rumped warblers depend on caterpillars during chick growth. If chicks hatch late, feeding trips increase while growth slows. This mismatch is like opening a cafeteria after the lunch rush. Food exists, but the timing reduces benefit. Insects adapt rapidly because their life cycles are short. Grasshoppers in the genus Melanoplus and many moth species complete development faster in warm years up to a limit. Development speed depends on enzyme activity. Warmer temperatures accelerate reactions until dehydration and heat damage intervene. Faster developers reproduce before plants and soils dry down. Slower developers fail mid-cycle more often. This resembles finishing a task before a shortened deadline. Completion matters more than size. Aquatic insects face strong selection from temperature and flow stability. Mayfly and stonefly larvae require cold, oxygen-rich water and stable substrates. When warm low flows increase, these larvae decline first. Their loss removes high-energy prey from streams. Rainbow trout depend on drifting insects to grow during short mountain summers. When drift declines, trout shift to smaller prey and growth slows. This is similar to replacing dense food with diluted calories. Intake continues, but energy return drops. Warmer water also holds less dissolved oxygen. Fish must move more water across gills to meet metabolic demand. That extra effort raises energy cost. Individuals tolerant of lower oxygen persist more often. Amphibians experience selection through breeding success. Sierra Nevada, yellow-legged frogs require ponds that last long enough for tadpoles to develop. When ponds dry early, entire cohorts fail. The population carries that gap forward for years. This is like missing a graduating class. The absence is felt long after the event. Reptiles respond mainly through behavior. Western fence lizards compress activity into cooler windows, feeding early and retreating as heat rises. Gopher snakes also shift hunting to mornings and evenings. Shorter hunting windows slow juvenile growth. Soil organisms adapt through dormancy. Many bacteria and fungi reduce activity when soils dry, then restart after storms. This works like placing machinery in standby mode. Output pauses, but damage is avoided. Dormant periods lengthen while active periods shorten. Nutrient cycling becomes pulsed rather than steady. Plants that capture nutrients quickly after wet pulses gain advantage. Slow responders fall behind as windows narrow. Mycorrhizal fungi also adjust. Network growth slows under dry conditions, limiting nutrient transfer to roots. Plants compensate by investing more in roots. Growth slows, but persistence improves. These adaptations interact across systems. Changes in plants alter insects, insects alter birds, and shifts in water alter aquatic food webs. Scientists study in long-term plots, observe reorganization rather than collapse. Systems settle into patterns shaped by constraint. Higher elevations remain cooler, longer. This slows adaptation and preserves older conditions. Lower elevations shift first. Differences widen along the gradient. Connectivity influences outcomes. Gene flow allows advantageous traits to spread. Isolated pockets lose options. Local loss accelerates. Time integrates these processes without spectacle. No single adaptation defines the future. Instead, many small advantages accumulate. Persistence reflects alignment with new limits. The landscape remains recognizable in form. Its living systems reorganize quietly within the same granite frame. Adaptation also appears through changes in energy use rather than appearance. Individuals that require fewer calories per day persist longer when food and water become unreliable. Among small mammals such as deer mice and voles, resting metabolic rate determines survival during prolonged dry periods. Lower metabolic demand reduces the amount of food and water needed to maintain body temperature and organ function. This functions like running equipment on a lower power setting. Output is reduced, but operation can continue longer before failure. Birds experience similar constraints through body mass and activity scheduling. Smaller individuals lose heat more efficiently at night and require less water during daytime respiration. Lower mass reduces evaporative cooling demand. Survival improves during extended heat waves when water access is limited. Nest placement becomes another selectable trait. Ground nesting birds that choose sites, shaded during late morning, avoid egg temperatures that exceed developmental thresholds. Egg proteins denature when temperatures rise too high. Shade keeps temperatures within viable limits long enough for embryos to develop. This is similar to storing perishable food in a cool pantry rather than direct sun. The contents last longer without intervention. Predators respond indirectly to these shifts in prey behavior. When herbivores concentrate in shaded or moist corridors, hunting success changes. Mountain lions encounter prey more predictably along these routes. Energy spent per successful hunt decreases because search time shortens. Reduced search time alters population pressure. Predation intensity increases locally without an increase in predator numbers. Aquatic adaptation is governed by oxygen availability and temperature timing. Fish that feed during early morning hours experience higher dissolved oxygen levels. Brook trout rely on diffusion across gill membranes to extract oxygen. Warmer water slows diffusion, increasing energy cost per breath. Feeding earlier reduces this cost. Energy gained from prey exceeds energy lost to respiration. This works like exercising when air is cool rather than humid and hot. Efficiency improves even if effort remains the same. Aquatic insects adapt through emergence timing rather than physiology. Midges and mosquitoes complete development earlier when water warms sooner. Earlier emergence allows reproduction before channels dry or temperatures exceed larval tolerance. Late cohorts fail more often. These timing shifts alter food availability for bats. Big brown bats experience earlier peaks in insect density near water. When peaks pass earlier, bats must extend flight time. Extended flight increases water loss through respiration. Individuals with more efficient kidney function tolerate this loss better. Survival advantage accumulates slowly across seasons. Reptiles show adaptation through thermal tolerance limits. Western fence lizards that remain active at slightly higher body temperatures feed longer. Body temperature affects enzyme efficiency. Activity improves until dehydration risk outweighs gain. This trade-off resembles working longer hours for overtime pay. Past a point, exhaustion cancels benefit. Amphibians face selection almost entirely through breeding success. Frogs that breed immediately after snowmelt succeed more often than those that delay. Tadpole development requires uninterrupted water duration. Shortened hydro periods eliminate entire cohorts. This resembles missing an entire planting season. The loss persists, even if conditions improve later. Soil organisms adapt through dormancy length rather than speed. Microbes capable of surviving long dry intervals dominate soil communities. Dormancy reduces metabolic damage. Activity resumes only when moisture returns. This is like shutting down sensitive equipment during power outages. Productivity pauses, but replacement is avoided. Plants interacting with these microbes adapt accordingly. Species capable of rapid nutrient uptake after re-wetting gain advantage. Roots with high surface area absorb nutrients quickly. Slow uptake strategies miss the pulse. Mycorrhizal fungi also adapt structurally. Shorter fungal connections reduce exposure to dry soil layers. Reduced reach limits nutrient transfer distance. Transport efficiency declines, but survival improves. This is similar to shortening supply routes during instability. Capacity drops, but losses decrease. Across decades, these small advantages accumulate. Population averages shift without clear boundaries. Long-term studies show convergence toward lower energy throughput systems. Productivity narrows, but does not vanish. Lower throughput means tighter margins. Populations persist closer to physiological limits. Generalist species tolerate this compression better. Specialists decline as conditions fluctuate. Elevation moderates these pressures. Cooler zones slow metabolic stress and oxygen loss. Adaptation proceeds more slowly there. Lower elevations show change first. Connectivity allows advantageous traits to spread upslope. Gene flow supports gradual adjustment. When corridors fail, isolation accelerates loss. Options disappear. Time integrates these responses invisibly. No single year defines outcome. Instead, repetition reshapes structure. Survival advantages compound quietly. The landscape remains familiar in outline. Its living systems operate under new internal rules. Adaptation does not restore abundance. It preserves function within constraint. The system continues forward shaped by efficiency rather than excess. What remains is what can operate within the limits. As systems adjust over long time spans, cooperation becomes as important as competition. Many of the most stable responses in Yosemite emerge through quiet coordination rather than conflict. One place this coordination appears is in plant communities sharing limited resources. Roots from different species often occupy separate soil depths, reducing direct competition for the same water. Shallow-rooted plants absorb brief moisture from light storms. Deeper-rooted plants draw from groundwater that persists longer into summer. This arrangement works like multiple shelves in a pantry. Each level is used differently, allowing more total storage without crowding. Fungi reinforce this coordination. Mycorrhizal networks connect multiple plants, redistributing water and nutrients across short distances. When one plant has temporary surplus, nearby plants can benefit. This sharing smooths extremes rather than amplifying them. Scientists observe this effect most clearly in mixed conifer forests. Pines, firs, and cedars maintain more consistent growth when networks remain intact. Soil structure supports this balance. Aggregated soils create channels that hold both air and water, improving root access. These channels form slowly as roots, fungi, and soil organisms interact. Once established, they persist across seasons. This persistence acts like a reusable sponge. It absorbs water when available and releases it gradually. Water movement through these soils is slower. Slower movement reduces erosion and nutrient loss. Streams benefit from this moderation. Flow becomes steadier rather than flashy. Steadier flow supports more stable insect populations. Aquatic larvae complete development with fewer interruptions. Fish benefit indirectly. Consistent food supply supports steady growth rather than feast and famine cycles. Birds feeding along streams respond as well. Predictable emergence of insects supports reliable nesting success. Meadows show similar coordination. Grasses, sedges, and wildflowers occupy slightly different moisture zones. This zonation spreads demand across the landscape. No single zone carries all the pressure. Pollinators benefit from extended flowering sequences. As one species fades, another begins. This staggered timing works like rotating shifts. Coverage continues without exhausting any one group. In Yosemite's higher meadows, this pattern is especially clear. Late melting snow creates overlapping windows of growth. Animals adapt to these rhythms. Feeding schedules align with predictable availability rather than constant searching. Mule deer adjust movement between meadows and forest edges. This reduces pressure on any single feeding area. Predators respond by spacing hunting efforts. Success remains steady without overuse. This spacing resembles taking turns rather than rushing. Efficiency improves through patience. Birds also benefit from coordination. Mixed species flocks forage together, increasing detection of food and predators. Each species contributes a different strength. Some detect movement, others locate seeds or insects. Together, the group functions more effectively. Risk decreases while intake improves. Soil organisms mirror this pattern. Different microbes activate under different moisture and temperature conditions. Some respond immediately after rain. Others become active days later. This sequence extends nutrient availability. Plants receive support over longer periods. The effect resembles staggered deliveries. Supplies arrive steadily rather than all at once. Fire also fits into this coordinated picture when it occurs at moderate intervals. Low-intensity fire clears excess material without disrupting deep soil structure. Regrowth following such fire often increases diversity. Openings allow new combinations of plants to establish. Animals respond positively to this variety. Feeding options expand without removing shelter. Over decades, these cooperative dynamics build resilience. Systems absorb variation without losing function. Scientists studying long-term plots in Yosemite observe this buffering effect repeatedly. Change occurs, but extremes are softened. Elevation continues to assist coordination. Cooler upper zones release water later, supporting lower areas indirectly. This delayed contribution acts like a reserve fund. Support arrives when lower elevations need it most. Connectivity allows these supports to function. Water, seeds, and animals move freely across boundaries. When movement remains intact, balance persists. Adjustment stays gradual. Time reinforces successful arrangements. Interactions that stabilize conditions repeat and strengthen. Less effective arrangements fade quietly. No crisis is required. The result is a landscape that feels steady. Change continues, but it is measured. Yosemite remains recognizable, not because it resists change, but because its systems share the work. Stability emerges from cooperation rather than force. This coordination also appears in how trees manage light. Different species occupy slightly different canopy heights, reducing direct competition for the same sunlight. Tall pines capture high light, while firs and cedars thrive in filtered conditions below. This layering allows more total energy capture across the forest. It works like adjustable blinds rather than a single open window. Light is shared across levels instead of flooding one surface. Leaves respond to this arrangement by adjusting orientation. Some tilt to avoid midday intensity, reducing water loss. That adjustment keeps photosynthesis efficient without overheating tissues. Energy gain stays balanced. Birds use this layered structure as well. Different species forage at different heights, spreading activity through the canopy. Warblers feed among outer leaves, while chickadees move closer to trunks. Crowding is reduced without reducing opportunity. This separation improves listening and watching efficiency. Each species focuses on a different zone. In Yosemite forests, this vertical organization is especially stable. Snow and moisture patterns reinforce consistent growth layers. Roots mirror this pattern underground. Fine roots occupy upper soil, while thicker roots extend deeper. Water uptake becomes distributed. Demand is spread rather than concentrated. This underground layering functions like multiple intake valves. Flow remains steady even when one source weakens.